So, let's get ready for honors chemistry. Starting with chapter 1. It's going to be a really fun year. One quick note, your book talks about the scientific method. That was section 1.2. I don't talk about the scientific method so much because what many researchers do in the real world is not how the scientific method is taught. So I'm not going to go over the book definition of scientific method, but just think of research is asking a question, doing a bunch of experiments to try to answer your question, but sometimes you don't even have a question, you just want to know what something is, or you want to know a measurement, so you do a bunch of experiments just to get a measurement. So I guess the question would be, what is the measurement of whatever you're trying to measure? But we're not going to worry about that. We're going to go straight to section 1.3, classification of matter, right here. So you probably have heard this before. Matter is anything that has mass, takes up space. Now, more important about matter is classifying it for chemistry's sake. So we can divide matter into 4 categories, far more than 4 categories, but for now we'll just divide it into 4. Pure compounds, and you'll have definitions a little later. Compounds are chemicals that have 2 or more elements in them. We have pure elements, that's just a pure element. A homogeneous mixture that has 2 different things in it, but you can't see the difference between them. It just all looks like it's one thing, but you have 2 distinct species in there. A heterogeneous mixture, there's 2 distinct species, and you can actually see, well, there's at least 2 different species. You can see both of them. So you could have, for instance, a heterogeneous mixture, sand and water. You can see the sand and you can see the water. They're different substances and they're mixed together, but you can see them separately. An example of a homogeneous mixture would be something like, I can't think of anything right now, salt water. So salt dissolves into water, and if you dissolve all the salt, all you see is the water, and you don't know that there's something else in there. So that would be a homogeneous. Everything looks the same. It's homogeneous. So here's how we classify. Does everything look exactly the same? If not, we have a heterogeneous mixture, and you can stop with the chart. But everything does look uniform. Everything looks the same in there. Then you have something that's homogeneous. Now we have to find out between homogeneous, pure element, and pure compound. We have different questions that will let us know which is which, or what the substance is. So, does it have variable composition? Meaning, are there at least 2 distinct substances in there? You would be told what was in there. You can't tell that you have a homogeneous mixture without doing some tests or being told something. If there are 2 different substances in there, variable composition means every single little molecule or formula unit in there is not the same. You have a homogeneous mixture if you have at least 2 different substances. If you have only one substance, you have a pure substance, and then you have to find out is it a compound or an element. Can it be separated into simpler substances, meaning, this would be by chemical means, can it be separated into 2 different elements, at least 2? It would be a compound if it has at least 2 elements. It would be just an element, a pure element, if there's only one element. So now we're going to classify each of the following. All right. Oops, I don't want to give you the answers already. You're going to fill these in. I'll talk through them. You should pause right now if you want to do this on your own. But if you need me to talk you through this, here's what we'll do. So just listen up. So you look at all these things, and you say, does it look uniform throughout? Does it look uniform? Yeah, it looks, they're all the same particles. They all look the same. It's pretty uniform in here. And so now we go to, it's uniform, it's homogeneous. Does it have variable composition? Meaning, does each formula unit, this right here is a formula unit. I'll use that word a lot. This is a formula unit. This is a formula unit. Are all the formula units the same? Yes, they are. So we do not have variable composition. Everything is the same unit. So it's a pure substance. Can we separate this into simpler substances? Well, we could separate these little gray balls apart into single gray balls, possibly, but they would all be gray balls. So we have a pure element. So I would symbolize different elements by different colors here. Now the next one Does this look homogeneous? Well, all of these are the same. So yeah, it's homogeneous. Some of them are rotated 90 degrees. It looks the same, so it's homogeneous. Does it have variable composition? These are all exactly the same. So nope, not variable composition. Can it be separated into simpler substances? Well, we could separate it into whites and grays, so yes. Therefore, we have a compound. So, oops. Oh, goodness. Sorry. Here we go. I'm wasting time. There's the answers for those. Okay, now this one, does it look uniform throughout? Now you're thinking about this macroscopically. Right now we're looking at this very microscopically. Is there an area that's only black or only gray or only white? No. These are all mixed together very well. So we're assuming if we were looking at this macroscopically from a big picture, it would look actually very uniform because even though we have 1, 2, 3 different things there, they're all mixed in together very well. So I would say that we would say that that looks uniform. It is uniform. It isn't really microscopically, but macroscopically it would be. So that's homogeneous. Variable composition, well, it sure does. There's 1, 2, 3 different kinds of particles in there. So there's definitely a variable composition. So that would be an example of a homogeneous mixture or a homogeneous solution. Oops, this should say homogeneous mixture because there are 3 different types of elements all mixed together well. Oops. Okay, now in D, notice how these particles are on one side and these particles are on another. That is representing that you have a separation between these. So physically, these you can see are separate from these, even though this is all together. So that would be our example of a heterogeneous mixture. It's not uniform throughout. So you don't have to have your answers written exactly how these are, but if you wanted to write them down, you could. Okay, physical and chemical properties of matter. So, some important notes. A physical property, you can observe it without changing the composition, without changing the formula units. So these would stay the same. These would stay the same. If I suddenly have a white and a gray separate from these, that would not be a physical change. So in a physical change, those formula units stay exactly the same. In a chemical property, oh, there's something going on out there. For a chemical property, you could only observe it by changing the composition or identity of the substance. So we would change, all of a sudden this would become whites, 2 whites and a gray, or 2 grays and a white, something of that nature. So let's do our example problems. And again, if you want to try this on your own, go ahead and pause right now and write your answers in the answer section. You can always change them, or you can wait. Now, this is single particles coming together to make doubles. This would be like A goes to A2. Now, did we change the identity? We didn't change the identity. It's still just little yellow particles. Still the same. This is a pure element. This is a pure element. But I did change the composition. This goes from A1s to A2s, meaning I have 2 particles. Okay, here's the explanation. So it's a chemical change because atoms are coming together to form a new structure of the element. The composition changes from A to A2. So that had to be a chemical change because we're changing the composition. Now here, let's see, we have, and again, pause this if you want to, do this on your own, or you can fast forward to where all the answers are showing if you want to do these and then check your answers. So here we have particles. We've got 6 particles, and they have a yellow and 4 maroons. And all of a sudden, the yellows are separated, and the maroons have come together to form, these would be diatomic, 2-atom molecules. And that would be considered a chemical change again, because we changed the composition. Whoops. Chemical change. We changed the composition. Now in this last one, let's see, do we change? Notice these are all particles that have 1 pink, and 4 maroons. And this would sort of be like a solid. They're all next to each other, okay? So they're very closely packed. It might be a liquid. Liquids take the shape of their container, but these are very closely packed particles, and now they're separated from each other. This is like a solid going to a gas phase. Notice I did not change the composition. It's still like AB4, not before like BEFORE, but A1, 1 pink, and 4 maroons, B4. So, and we didn't change the identity, we just changed the phase from solid to a gas. So that would be a physical change. All right, moving on, measurement. We use the SI, System International, in chemistry for, yeah, pretty much for everything. So in the SI system, we use grams for mass, meters for length, and liters for volume. And notice length cubed or meter cubed is also used for volume because volumes are lengths cubed. And then you'll need to know these prefixes right here, kilo, deci, centi, milli. You only need to know 4 of them. You must know kilo. When you see kilo before a unit, this would be a kilogram. You just replace the kilo with 1,000. So that would be 5.2 times 1,000 grams. The deci means 0.1, so you'd have the 5.2 times 0.1 decigrams. Centi is 0.01. So, and this one's easy because like a cent of a dollar, 1 cent is 1/100th of a dollar, so that's always really easy. Anyway, so centigram is times 0.01, a milligram is times 0.001. Those are the only ones you need to know. All right, so do the following conversions. You can pause if you want, or I'm going to also just show you how to do these. So this should be kind of straightforward. So we'd have 4.8 times a milli is 0.001. So we'd have 0.0048 grams. And we have 0.14. Kilo is times, pause this if you want to do these on your own. Kilo is 1,000, so times 1,000. So we'd have 140 meters. Meters to decimeters, we have, oh, this is different. We're going from meters to decimeters. We're going to have to do a conversion here. 0.38 meters. And then in 1 meter, we have how many decimeters? Decimeter is 0.1 meter is 1 decimeter. So that would be 0.038 decimeters. We're just doing a little conversion there. We'll learn conversions more in another section. 45 milliliters. Milli is times 0.001. So we have 0.045 liters. And I'm not sure on part C. I was retyping everything. I might have written this wrong. That is 3.8 decimeters. I'm not sure exactly what I wrote because I've erased all of the writing now. Okay. Density. Just real quick discussion on density. Density is mass divided by volume, and you'll be expected to be able to use this equation. If I give you a density and a mass, you should be able to solve for volume. Given a volume, solve and mass, solve for density, et cetera, et cetera. But some important things about density. If substance A floats in substance B, which is more dense? A floats in B. B is more dense. If A sinks in B, A is more dense. So substances float in substances that are more dense than they are. All right, now to some of the meat. Handling numbers, scientific notation. So this is just giving you a general idea of why we use scientific notation, and I want you to write the following in scientific notation. And you should be able to pause and do this on your own. I will show you real quick what you do, but basically you just move the decimal. So the decimal's here, and we go 1, 2, 3, 4 to the left. This would be 5.6 times 10 to the 4th. If you move the decimal left, the power on the 10, the exponent, is positive. if you have to move the decimal to the right, the power on the 10 is negative. So I'm going to pause this, and you're going to see the answers in just a moment, so you should pause. And there are your answers. You can pause if you... So we're going to talk about significant figures, aka significant digits, or sig figs as I call them. We're going to look at this ruler right here, and we're going to talk about sig figs and how they work. They're always about measurements, and they include the measured digits and one estimated digit. So we're going to look at this first arrow, and you should notice, I'm going to bring this up a little bit, you should notice that the arrow is very slightly to the right of the 0.9 centimeters. So we would write that, as 0.91 centimeters. The 9 is actually measured. We see that we're right near the 0.9. And then we're estimating this one placeholder right here. The 0 is just saying how big or small the measurement is, so the 0 doesn't count as a sig fig. The 9 and the 1 are the significant figures, the 1 measured number and the 1 estimated number. The middle arrow, let's make this bigger again. Whoops, I made that way small. Okay, so we know that we have 3.7. This right here is 7. So those are the two measured digits, the 3 and the 7, 3.7. And then this arrow is about halfway between the 7 and the 8. So I would call this 3.75, where I am estimating the 5 right here. So this is my estimated digit, and these two, the 3 and the 7 are my measured digits. That would count as 3 significant figures, or 3 sig figs. Now this last one, notice it's falling right on the 5. It's right there, right on the 5. If I just write the number 5, that's not giving you the information that the arrow is falling exactly on the 5. It's saying the arrow is falling somewhere between the 4 and the 6. If I write 5.0, just the 5.0, the 0 and the 5 here, then I'm saying the number is somewhere between 4.9 and 5.1. So I'm actually measuring the 5 and the 0, and I'm estimating that last 0, because that arrow is falling right on the 5, not just a little less, not a little bigger, right at the 5. So this would be written as 5.00 centimeters and would be considered 3 sig figs. Summary for this is that leading zeros up to the first measured digit do not count as sig figs. So this leading 0 right here is not a sig fig. Trailing zeros are significant only if a decimal is written. All other digits are sig figs, including zeros in between the last 0 and the first, between the last and the first sig fig. So the first measured number, so here's our measurement, 145 centimeters. So here's my first measured number is the 1. And over here, my first measured number is that 2. These leading zeros, they're not significant. Those leading zeros are just, showing you how small that is. So the first measured number is a 2 here. Here, we don't have any leading zeros, so that 2 is measured. This 3 is measured, and that 8 is measured. So I'm just writing down the first measured number in here. And the next row, we're going to have the estimated digit. Actually, before you see that, go ahead and pause if you want to fill in this whole chart on your own. The last digit, typically, is your estimated digit. So you should have paused, because your answers are showing right now. Pause. Okay, so 5 is the last measure. Oh, well, that's the estimated, sorry. The 7 is estimated. The 0 is estimated. The 5 is estimated. And that second 0 is the estimated digit. Okay, your last digit is your estimated digit. Now, how many sig figs? Again, pause if you want to fill this in yourself. So this would have 3. These zeros, leading zeros never count. So 1, 2, 3, 4 sig figs. No leading zeros. Trailing zeros count if there's a decimal printed, and there was. So this is 4 sig figs. This is 4 because the leading zeros never count. This is 3. Trailing zeros always count. Zeros at the end, trailing after the last non-zero number, count if there's a decimal showing. Okay, that's easy. Now, mathematics with sig figs. This is different. There's a couple rules. When you're adding or subtracting numbers, you round the answer to the least precise estimated digit of the numbers. I'll explain that with an example. When you multiply or divide numbers, you round the answer to the smallest number of sig figs in the problem. So here's some examples. When you add these two numbers, do this on your own if you think you can. Go ahead and pause. So we're adding, we'll use that. We'll round the answer to the least precise estimated digit. Well, here the 6 is estimated. Here the 1 is estimated. Now, which is less precise, tenths or hundredths? I'm hoping you know that tenths are less precise than hundredths. If you measure something all the way to the hundredths place, there's more precision than measuring just to the tenths place. So you add these numbers and then you round to the tenths place. And here's your answer. There you go. 24 centimeters. 22.4 centimeters right there. Okay, try this one. So here we're in the 10,000ths place, I think, and here, I don't know, we're farther along. This is more precise, this placeholder right here is more precise than this placeholder right here. So when I add these two together, I will round to the 10,000ths placeholder. So here's what it looks like. Pause if you want to do it on your own. There we go. So you add the numbers together, and then you round to the less precise estimated digit placeholder, the 10,000ths place. All right, multiplication. Now on this problem, let's see, what is our rule for multiplication? We're not looking at placeholders. Multiplying, dividing. We round to the smallest number of sig figs in the problem. So in this problem, I have 2 sig figs. Do these zeros count? Yes, they do. They're not leading zeros. They are trailing zeros and a decimal showing. So I have 2 sig figs, 3 sig figs. I will multiply the answers. I will multiply the numbers, and then I will round to the smallest number of sig figs, which was, remember this had 2 and this had 3. So I'll round to 2 sig figs. And do I have an answer showing? No, I'll put that up. All right. There's my answer right there. So there were 2 sig figs, 3. That means I need to keep 2. And when I multiplied these, it actually came out to just 2 sig figs. So that worked. If I needed to keep 3 sig figs for whatever reason, if it turned out that I needed to keep 3 sig figs, I would just write this as 86.0 to make it 3 sig figs. So you can add zeros at the end or turn your number into scientific notation. If you're having trouble with figuring out how to write the number with the correct number of sig figs, you can just always write your number in scientific notation and add trailing zeros if you need more sig figs. Notice I have millimeters squared because I have a millimeter times a millimeter. Always keep track of your units. You will lose credit if your units are wrong. So I have a millimeter times a millimeter, which is a millimeter squared. On the next problem, make sure you keep your grams per liter in your answer, and make sure you divide. I multiplied these at first. Pause if you want to figure it out on your own, but here's the answer. So I divide these numbers, and I get this long number. This had 3 sig figs, this has 4, so I want to keep only 3. So I round this to 3 sig figs. Now remember the leading zeros don't count as significant, so I just leave those alone. And here's my first sig fig, second sig fig, third sig fig. And the 7 I will round up because the number after it is 5 or larger. So that's 0.000138 grams per liter. I can also write that in scientific notation. I didn't tell you you needed to, but it's good to just get that practice. And that's it for this video. We'll do dimensional analysis on